Thank you, Salvatore. Good morning, everybody, and thanks for the organizers for giving me this opportunity. Okay, it's not a good idea to give the first talk after dinner. This is something that we all know. So, in the next 2 hours, I'm going to describe what's the situation concerning tensions and modified gravity, right? So, let me just sketch the main idea that the history of astronomy and cosmology, history of science in general, is a history of tensions. So we have theories, we make predictions, we go and describe the data. However, the advance of technology gives us new data that put our predictions in tension, and at the end of the day, we have a paradigm shift, and we construct a new theory that can describe the new data in a better way. This goes on and on back to ambiguity. And the question is, do we live in such epoch today? So, will these tensions bring us a new paradigm shift of new physics? So, let me go back where gravity started. So, the first, as we say, astronomical and cosmological model was the Aristotelian model, right? So, we have the Earth as the center of the universe, we have all the planets rotating around it, they made by earth, fire, water, and air, and the space itself is made by the fifth element, the Greek datasets, right? And according to these gravitational theories, heavier bodies fall faster. Now, this scientific theory was in so incredible agreement with the data that it's the most long-standing scientific paradigm in history, and it became working for 1,500 years, right? So, what happened is that in the Middle Ages, the advance of technology slowly gave us new data, and the first data arrived from Arabia Observatory, from Persian and Arab scholars, and they started putting into troubles the details of the Aristotelian Ptolemaic model, which before that, you know this whole story about the epicycles, that in order to fit new data, they assume that planets are doing a very peculiar motions. However, the real revolution with the data came with Brucker and Kepler when they spent 13 years of their lives in order to observe the motion of the planets. So now the data are so accumulated that they force us to abandon the Aristotelian Ptolemaic model and establish, as you know, heliocentrons with elliptical objects. Now, concerning experiments, as you all know, Galileo Galilei made the first experiment. So it's incredible if you think of that. For 1,500 years, nobody had thought to put Aristotelian analysis into question. So he was the first one to do the experiments in an organized way and found that bodies fall with the same speed, independently of their mass. So we have observational data from Brucker and Kepler, experimental and observational data from Galileo. So Newton came and gave us new physics, the paradigm shift. And Newton said that I was able to see it very far away because I was sitting on the shoulders of giants, meaning the observationalists and the experimentalists. So now we have a theory of gravity, and Newton understood that it's the same force that makes apples falling on Earth and the same force that makes the planets rotating around the sun. It's the force of gravity. And this is the first time that we understand that in order to have an astronomical model, we need to have gravitational theory, because gravity is the director of the dynamical evolution of the celestial bodies. Okay? Now, Newtonian gravity was in perfect agreement with observations for many, many years, up to the level where new technological advance gave us the ability to collect new and more precise data. So 1859, we discovered the anomalies in the Mercury's motion. Okay? And as you know, and we learned in school, Einstein came out with a new paradigm shift, general relativity. I want to mention two things. First, oops, so this pointer doesn't work. Okay, 1859, observational discovery was made. GR came out in 1915. So for 60 years, two generations of physicists were living under tension between predictions of Newtonian gravity and the new data. So it's not an automatic procedure if you have a new data to change your theory. It was there for 60 years, and actually, okay, we know the result. We know Einstein, General Relativity. But all the good physicists that we know, Lorentz, Kelvin, and the others, had proposed gravitational theories, different than Newtonian gravity. We know the answer, which is GR, but just to let you know, during the tension time between theoretical predictions and data, there were many, many theories. And of course, as you know, the majority proposed that there was an extra planet, Vulcan, a planet that we have not seen, so in a sense, a dark planet, that in the framework of Newtonian gravity was causing the anomalies in the Mercury's motion. But these theories did not predict this 43 seconds per century. They gave less numbers. Right? And similarly, Michelson-Morley experiment about the speed of light, 1887. Special relativity was put forward 9.5. So again, for 20 years, physicists lived in this tension time between theoretical predictions and the new data. And it took us 20 years to propose it in new physics. So we have to have this in mind, that history of science is a history of tensions, and the transition to the new physics, to the new paradigm, is not automatic. Okay? It takes time, and during that time, many people, many physicists, many scientists proposed theories in order to solve these tensions. And of course, GR came out of this way. You are all familiar with that. I'm going to talk on the details of that. So gravity is geometrized and it's described by a curvature. The curvature of space-time describes the gravitational interaction, right? So this is the reaction. These are the field equations. This is the energy momentum tensor. By the way, GR was the last atomic, the same personal theory of one person and the first collective theory, because many people contribute to that. We need to remember that, because science today is a collective phenomenon. Now, GR is in perfect agreement with observations, right? Either in the lab or in the solar system experiments or in observation. However, technology advanced, and this is the summary of observations of the 20th century, right? So, we're living in a tiny part of a huge universe. That's why we have the inflationary model. This is a standard model of particle physics plus the Higgs. So these are the dark matter possible particles. And this is the thermal history of the universe. And this is the composition of the cosmos today. You are all familiar with that, right? 25 dark matter, 7% dark energy. So all these are the observations that we had the last century. Now, this observation gave us standard model of cosmology, which is an almost perfect model. Okay, you know, so these are the two Friedman equations assuming the cosmological principle, which is number one starting point of cosmology. So you put the fluids, and this works perfectly. It describes the thermal history of the universe and all the different epochs. Now, in particular, it describes the background cosmological behavior of the universe. So assuming, neglecting the details and zooming out, the universe is homogeneous and isotropic, and you can describe that and with these fluids, and of course you make predictions, for instance for things like the Hubble function or the test parameters or the equation of state parameter of dark energy, and you confront it with data from supernova, baryonic oscillations, you see the CMB6 parameter, and then you check your theory. Now, after you describe the universe at the background level, you go to a more subtle analysis. So you zoom in, so the universe starts becoming inhomogeneous and anisotropic because we have these perturbations. So you're all familiar with that. You quantify that with the matter of the density. So in a completely homogeneous and isotropic universe, delta is zero. In the real universe, it's not zero. So we have this delta. We have the Poisson equation. So at the end of the day, you do the perturbation theory, perturbing the geometry and the matter sector, and after some parameterizations, you have the equation, the evolution equation of this delta, right? So now we can define this famous observable, the sigmoid, which is the time-dependent root mean squared fluctuation of the matter density field inside spheres of radius 8 megaparsecs. Why 8 megaparsecs? Because we want to be a linear regime. So we make predictions for this guy, and then we compare it with the data. So lambda CDM is very efficient in describing the universe both at the perturbation level. Okay? And of course, you can have all kinds of data sets describing that. Now, let's go to the 21st century. Astrophysics and cosmology have become precision sciences. It's amazing the accuracy of the observations that we have to do and the amount of data, and we can have, you can see here the evolution of the length of the telescopes on Earth, and of course we can have many satellite telescopes. So we are even space gigantic things like LISA, and we collect a huge amount of data. Right? Data that we could not even think to collect 20 years ago. And this data puts our standard model of cosmology into questions. First one, at the theoretical level, GR is non-renormalizable. So this means that general relativity cannot be put together in the quantum framework with the other three fundamental interactions. And this is a serious problem. I know that in astronomy or astrophysics you can neglect that, but this is a serious issue, that you cannot describe gravity at the quantum level. I mean GR, and you start from GR. Of course, the cosmological constant problem. Again, many people say, okay, lambda works, so we don't need to ask questions about that. No, because if you try to calculate the value of lambda according to any knowledge that we have of quantum theory, we get an error of 120 orders of magnitude, right? And this is the worst error, not only in the history of physics, not only in the history of science, in the history, full stop. This is the worst error. Although believing that the Earth is flat is an infinite error, but okay. So we cannot hide this under the carpet, right? What is the value of the cosmological constant? Now, primordial universe, again, we need inflation. I don't have time to talk today because we have the horizon problem, flatness problem, monopole problems, and other problems. So we need inflation, but what causes inflation? Inflation is an external mechanism on top of lambda CDM. Okay? Is it a scalar field? And what happened with the scalar field? Is it modified gravity? So you see, you start thinking new ideas. So if you apply these new ideas in the early universe, why not applying them in the late universe as well? Dark matter. What the hell is going on with dark matter? Where is this particle that we're searching for decades? So this is again an important issue. And of course, H naught and sigma tensions, I will spend some studies on that. And this is a picture from Leandro's review on all the problems or the questions of lambda CDM. And as you can see, there are not a few. And the reason that we have these issues is because we have new data. New data gave us information about the dipole anisotope, the possible, the lithium problem, or the core spot, etc., etc. So we should not hide them under the carpet. I will not spend so much time because you are all experts on that. So H naught tension, the value of H naught estimated from early universe and Planck observations, assuming lambda CDM cosmology, is less than the values that you obtain from local measurements. Right? And here you can see from our review all the data sets. And the problem is that, okay, the error bars, so according to time, it seems to get worse. So if this is not something systematical, there is something very, very curious, we need to change something, right? So we need to introduce a kind of new physics, either at early times or late times. And there are many models I will show you, or of course modifications of gravity, and you are all familiar with that. So we have this expression, this is the sound horizon, this is the angular diameter distance, so you can change one of them or both of them, and okay, this is not completely robust, but just qualitatively, these are called early time solutions and these are called late time solutions. So people are following these procedures to solve it, and the sigma tensions, again, that you are all familiar with that, so there seems to be less clustering than expected. right? And again, of course, here, as we heard from Marika and others, I mean, we can have systematics or we can reduce the tension, but there seems to be something here. Although less severe than the H-notch tension, of course, this is where I meant, you can have the double counting in the data, so you need to be very careful or model dependent. But if this is not systematics, again, we need to modify something. And you can change either there, the universe assuming new properties for dark matter or interactions or whatever, or modifications of gravity. So, these are the solutions. I can stop here. These are some solutions that you can find in our review of many of you were co-authors, solving both tensions or one of the tensions or the other tensions as well. You can see that there is a list of possible solutions here. And of course, you can have other more radical solutions. And of course, as you probably thought, the fact that we have 200 solutions for the tensions means that we don't have a solution, right? So, and this is the review that I suggest you to read about all this kind of stuff.
So the book appears, right?
So, what, sorry?
There's a book, an encyclopedia.
yeah. Okay. However, I mean, just we need to be careful when we are solving one tension, not to spoil the other tensions. This is very important, right? So these are the 10 commandments of the tension solving. Okay, if you are familiar with statistics, go and read that. But it's important not to rule the other tensions when we're trying to solve one. Okay, let me now give you a kinematical model independent guide how to solve that. Now, in order to solve the H-naught tension, one of the solutions could be that we need a mechanism to give us faster expansion today. So we need something new in the Friedman equations. Now, concerning the sigma A tensions, these are under the known assumptions. These are the evolution equation for delta. Here, in general, we have an effective Newton's constant, and here, in this friction term, we have the Hubble expansion. So you could think of changing this G or this H in order to bring delta to your to the amount that you have. So, for instance, let us put in the so on top of lambda CDM, suppose that we have one theory that gives us this correction, this delta. So you can use the data to reconstruct this delta. Sorry, this D. Okay? So you assume that at early times you coincide with lambda CDM, but according to the data, at late times you need this non-zero D. Okay? So you can reconstruct that. And the question is, what kind of theory could give you this? Now, one way to think of that is if we touch gravity. So if we have, qualitatively again, if we have a weaker gravity at sufficient intermediate scales, weaker gravity means faster expansion, and weaker gravity means less last time.
Where did you get this equation to, right? So
No, I made it. It's a random equation. Sorry, I want an H of Z, which is just a correction on lambda CDM.
Where's the integration of this?
No. I mean, you can think that this includes here. This is general function.
Fine.
Okay. Now, I will spend 1 minute here, and this is something I want to get back home, even if you are not working on theory, even if you are observational. GR. Let us understand how GR was made, because if we want to change it, we need to understand what is hidden in general relativity. Now, general relativity has some inputs that are needed for theoretical consistency. On top of that, it has some inputs that are assumptions coming from good observational guesses. So good, well guesses, educated guesses, assumptions. And it has some completely arbitrary assumptions. Okay, let us see one by one. Differomorphism varies. Of course, we need that. We need the physical laws to be general covariant, etc., in order not to have, you're all familiar with that. So we need that. Now, space-time dimensionality. this guy here. How do we know that? This is a good assumption because it's in agreement with observations, but there is nothing fundamental about that. Because we check things, I mean, you cannot check the space-time dimensionality below 10 to the minus 30 meters, right? Okay, we check it today, so this is a good assumption, but it's not something fundamental. Again, geometry, curvature. This is a completely arbitrary assumption. Einstein had this idea that gravity is geometry, but at that time, the only geometry that was there was Riemannian geometry, so he used Riemannian geometry. However, we now know that there are many more geometries, so this is one arbitrary assumption. It works, but it's completely arbitrary. Technically, this is done by assuming the Leibniz-Vita connection. Now, linear needs scalar. Why? So even if you accept that gravity is curvature, why to use a linear term? Again, here, because as you know, in the history of relativity, it was first a question of motions that were discovered. So Einstein thought, okay, in the right-hand side I will have the energy momentum tensor, this 4x4 matrix G nu, so I need to construct a geometrical object, so G nu, the Einstein tensor. And then they were trying to find the action, and you know the story about Hilbert and Einstein that they published that with some days of difference. We have the Einstein-Hilbert axiom, right? But the question is, why Einstein assumed second-order field equation? He did that in order to avoid having all this Cauchy problem and all this instability issue that we now call stochastic instabilities and all this kind of stuff. If you assume second-order field equations, then you are sure that you don't have any problem. However, the opposite is not true, because you can have higher-order field equations that are safe and healthy. Why? Because these higher orders mean that you have a new extra degree of freedom with second-order field equations. So Einstein missed Evo bar because he didn't want to have more than second-order field equations, but you all know that, for instance, Evo bar is a healthy theory, right? And of course, metric compatibility, again, this is a good guess from observations because we don't get a different redshift, for instance, looking at different times. So, if you don't have metric compatibility and you parallel transport a vector, the left changes. So again, we have a good educational guess for that. Minimal matter coupling. This is also something that is coming from observation. Equivalence principle. Again, this is a good observational assumption. There is nothing fundamental in that. Lorentz invariance. Again, we test it. So at the level of experiments, it's good, but there is nothing fundamental of that. And locality and other things. So there are many hidden issues there. And the question now is, okay, this is the most successful theory of humanity. Standard model of particle physics, and this is GR. So it's almost impossible that this is the final theory of gravity. This theory makes predictions up to the 12th digital number, right? So there are some people saying, okay, instead of trying to expand this and find the fundamental theory of gravity, let's try to reduce that in a very compactified theory of gravity. However, this is not the case. Nature is not simple. This idea comes from Pythagoras, that nature should be simple at the fundamental level. As we dig, we don't find that. And actually, as Parmenides used to say, the fact that exists something instead of nothing is already an infinite complication, right? So, there is no fundamental reason why gravity should be very simple. And this is just a sketch of the various ways, breaking one by one all the assumptions that I told you. The zoo of modified theories of gravity from the book that we wrote in Canada some years ago. So I will spend 5 minutes for its theories. No, I will just give you some basic examples. First is you can add higher order curvature invariance in your Lagrangian, going to F of gravity, F of Gauss-Bonnet gravity, level of gravity, Weyl gravity, on all this kind of stuff. You can add scalar vector tensor degrees of freedom, going to this class of modifications, when we have all these scalar tensor theories, Quintenses, Brownian, Galileos, Hordensky, beyond Hordensky. You can add vectors here, like in Einstein network theory, or massive gravity by gravity. By the way, massive gravity is the most reasonable modification of gravity that you can think of. It's not the simplest one because it has 5 degrees of freedom, but it's the simplest one. If I give you a scalar Lagrangian and I'm asking you to modify that, what is the first thing that you are going to do? To add a massive term. You are not going to think of changing the dimensionality of space-time. So that's why it was discovered in the 30s. It was one of the first theories. You can go to advanced geometry using normativist non-Philistine geometry. Here is the torsional thing that I will spend some time because I'm running out of time. I will describe the solution to the tensor, a possible solution here. And of course, you can have extra dimensions like in breakboard and string theory, or you can have more radical modifications of gravity is an emergent phenomenon, right? It does not exist at the fundamental levels like temperature. It arises due to the increase in the complication. It's a statistical effect. Like temperature, it does not exist if you have one particle. However, in thermodynamics, it arises. So all these are possible modifications. So the second thing that you need to know is if we want to modify gravity, if we are convinced on that in order to solve the theoretical and observational problems, then we have a huge number of ways. So what the community is doing is take all these theories and you confront it with the data. This is what we're doing. So I will start, how much time do I have? Salvatore, you like Plato, eh? But how much? I have 10 minutes? 10 minutes. Okay, good. Okay, so this was written in Plato's Academy, the first university in the world, that those that do not know geometry are not allowed to enter. So this was to give the fundamental implication that geometry has in all kinds of knowledge. So I will just give you one of the examples of how modifications of gravity could elevate the tensions, right? So as I told you, qualitatively, we know what is the h of z that we need to reconstruct. And let us propose one of the theories. This is just a sketch, right? So I will put forward this idea of using torsion. Now, as I said, in GR, gravity is geometry, geometry is curvature, so gravity is curvature, right? So as Wheeler Beautiful says in his book, matter tells space-time how to curve, and the curved space-time tells matter how to move. Okay? Technically, this means that you are using the Leibniz-Vita connection, which by construction, it has, because it's symmetric, it has zero torsion and only curvature. So in GR, gravitational information is embedded in curvature. Okay? Good. Now, later on, Einstein had the following idea, that curvature describes gravity, but torsion describes electromagnetism. So using both geometrical concepts, curvature and torsion, we could have a unification of gravity and electromagnetism. However, in 1928, he found out that torsion does not describe electromagnetism. Torsion is an equivalent way to describe gravity. So, and he named this theory teleparallel gravity. Actually, teleparallel, Einstein was not good in names, like in General Relativity. Teleparallel is the way that you define parallels at a distance. So in this theory, gravity is geometry, but geometry is torsion, so gravity is torsion. And technically, this is made by using the Weisel connection, which by construction it has only torsion and not curvature. You see, this is something that we need to understand. The metric from the Greek word to measure helps us to measure angles and areas on the manifold. But there is a completely dependent concept, connection, which defines the parallel transportation. The way you define your parallel transportation is completely dependent from the way you define your metric. So if I give you a manifold, and I'm asking you, what's the curvature and torsion of this manifold, what is the answer? The answer is that there is no answer. In order to find the curvature and torsion, I need to define the connection. So in this kind of theories, of course, a little bit more technicalities here, we use the tetrad field, so these are the four hormonal bases on the tangent base, and these are connected with the metric with this expression. And we can define now the Weisel connection instead of the Leibniz-Vita connection, and we can define the torsion tensor, and from contractions of the torsion tensor, we define the torsion scalar. And this scalar is the Lagrangian of the theory. You see in a similar way that in GR, we have the Riemann curvature tensor. From contractions of this tensor, we have the Ricci scalar, and the Ricci scalar is the Lagrangian of the theory. Now, if you take these two theories, you get the same equation. That's why Einstein called this theory telepar equivalent of general relativity. And of course, now you can start from that in order to build modification of gravity. in the same way that we are doing in Kevac's gravity. Like, you take GR and you upgrade R to a function f of R. So let's do the same thing in torsional gravity. We obtain this theory, and these are the Friedman equations. Important thing, although GR is completely equivalent with the part equivalent of GR, their extensions, their modifications in the naive way that we're doing in the literature are not equivalent, right? So this is a new gravitational theory with no known curvature equivalent. Now, we are using this theory in order to reconstruct h of z and g of z in order to solve the tensions. So we assume an asset of this form. So this is gr, this is a constant, the cosmological constant, the integration constants, and on top of that we have these corrections. So we plug this in our equations in order to see what is needed in order to solve the tensions. With the qualitative arguments that I told you, the important thing to know is that in modified theories of gravity, you get an effective Newton's constant, you see? So I can play with the functions in order to have a weaker gravity, in order to improve both tensions, and in particular H0 tension. And of course, if you reconstruct that, you can obtain, you see, weaker gravity at sufficient intermediate scales, and in the end of the day, you can alleviate both tensions. So these reconstructing models, corrections on top of lambda CDM coming from power law torsional corrections, they can alleviate both tensions, and these are in agreement with the data. Now, you can see that here, this is a paper we wrote with Spiros and Leandros, that this is possible in this series of gravity. You can obtain weaker gravity. So weaker gravity can solve the tension, which is not possible in other modified theories of gravity. You see, in Evohar gravity, if you want G effective, here it has a mode dependence as well. However, in these theories, G effective is larger, because if it's not larger than G, you have Gauss. So then weaker gravity at the sufficient level is not something that you get trivially. Now, in order to start summarizing, so this is just one model of modified gravities. You can play the same game with all the others, but I chose torsional gravity just to take something back home. So if we have modifications on top of lambda CDM, you can make H0 larger today and also alleviate the sigma A tensions. And of course, you need to check all these kind of models from all kind of data, from solar system, galaxy data, galaxy cluster, and of course, cosmological observations. And this is plot, I don't know if you can see that we wrote with Eleonora in Nature last year, that you know this Lego story about the cave, that we are scientists here having our laptops. We are in the cave making observations, the cave of Earth and our galaxy. We cannot travel the whole universe, and we are trying to understand what's going on by observing our data. However, the real world can be different, and this is our goal as a community, trying from the data to reveal the fundamental theory of nature, and according to these modifications, the fundamental theory of gravity. And before closing, a little bit of propaganda. As you all know, I mean, with Eleonora, Jackson, Salvatore, and Spiros and Olga, we organized last year the conference Tensions in Cosmology in Corfu in Greece. So this was solely dedicated to all kinds of tensions. We had good discussions. And this year, in September, we're doing the second round of that. So you are all more than welcome to join and discuss all these things. So, thank you.
So, Lenis, we've got 100 years of GR literature, right? Yeah. So we modify GR. Every paper that you've written in GR, you really want to do that in your modified theory. You want to show that there's a Schwarzschild solution. You want to show there's a Kerr solution. You have to do a whole lot of things, the whole scalar Bible, the solar system, all that has to be done. And once you've done that with your model, then you can start talking about cosmological tensions.
Right? I totally agree.
Now, so where are all these tests?
That's why there are thousands of papers in modified gravity, because people are doing that. If you have,
but let's give a list of things that you would like to do first before you get to these engines? Where would you start?
No, I mean, from solar system data, I mean, from, all kind of experimental things in the lab, but also in cosmology. For instance, BBN. BBN is a very nice case to kill theories, because if you modify the gravity now, you don't want to spoil the success of the early universe. Inflation is another thing, and by the way, in inflation, modified gravity is favored, right? Starobinsky inflation is the most well-fitted model with the data. So I agree with you. You have to do all analysis from black holes to cosmology, and this is what we're doing. And if you ask me, the future will be machine learning. I mean, we want the machines to do that for us because we don't have time.
So it would be nice if we had a slide where you basically sort of say, well, we want to pass these checklists first.
In some other talks, I'm giving these slides.
We're going too quick with this, right?
Sure. No. And gravitational waves.
No, I think we should.
Okay.
Yeah, just a comment. And gravitational waves is also a very, very good starting point.
Yeah. So, please tell us something about gravitational waves. What's going to be the direction that we should that we need to follow? To understand better,
This very good. Okay, so the question is, for Zoom, about the gravitational waves. Of course, gravitational waves is the new tool that we have in order to test GR and of course test modification of gravity, because it's extremely powerful. It does not depend on astrophysical assumptions, and it can really give you smoking gun. For instance, if we observe extra polarizations, this will be a smoking gun of modified gravity. Even, you see, with the multi-messenger astronomy, we have one data point, this neutron-star measure that gives us the information that gravitational waves move at the speed of light. So only one data point killed half of these theories that I was telling you, because in general modified theories of gravity, they predict gravitational wave speed different than the speed of light. So gravitational wave, for us, it will be the real thing that we need to do. That's why we are all involved in LISA. So in 2037, it will be on board, and we will be able also to touch the primordial gravitational wave spectrum. And all these are sensitive in the underlying theory of gravity. So yeah, this is very important.
Now, I want to extend a little bit the Evan's question. And I think the first thing, the list that you mentioned before, is actually the existence of screening mechanism. Because if you don't have a screening mechanism, you cannot really have effects of cosmology without rolling things out in the system. So which of these theories have screening mechanism built in? Again, from one theory, we know that.
Yeah, very good. So this is under research. EVOVAR, for instance, another curvature gravity, they have it. In EVOT, we also have it. You see, if we have the extra degree of freedom, because these theories can have more than one extra degree of freedom, you can find the screening mechanism, but I totally agree, of course, that you should not spoil the solar system physics, so you need something happening at the local scale. And this is under research. I mean, as you both say, if you have a new theory of gravity, then you need to do, 50 papers, one by one, checking all these things. It's a hard procedure, right?
So when we fit data, there's a penalty we pay, right? We calculate a chi-squared or something like that, right? So there's a naturalness element, right? In some sense, in data picking, right? Again, in modified gravities, you should have some criteria of saying these theories are more contrived than these theories, and we should start with these theories first, right?
Yes.
So again, you really have to start with GR and move out and
Exactly. So in these theories, typically you have extra parameters. So in the end of the day, in the Friedman equations or in the perturbation equation, you have extra parameters. So you fit with the data and you find the contour plots of these extra parameters. And then you impose information criteria, i.e. to big or deep, in order to compare with lambda CDM. To be fair, lambda CDM seems to win in most cases, but not all. There are cases of modified gravity or interacting cosmologies that are better than lambda CDM. So this is an open procedure. We have all the machinery to do that, and in the end of the day, you may exclude completely theories. There are many theories that are completely excluded, but there are also viable theories that survive.
Okay, thank you, Manos.